Hello students, so in this session let us discuss about the stress, strain and different types of stress and strain, right, and the relationship between them. So let us discuss about stress first. What is stress? So stress is defined as it is the internal force per unit cross section area. Okay, internal force developed per unit cross section area of the body when subjected to external force. So basically it is same as force by area, which you call as pressure, but the symbol here will be sigma. Sigma is the symbol for stress. Now this force, we are saying that it is the internal force, but magnitude wise this force F, which is the internal force, you can write FIN. FIN means internal force. This FIN is same as F external force. So magnitude wise they are same only, right? Magnitude wise it is same. Okay, but there are different ways we can calculate stress, but let's also see strain here before we go into that. So strain, which is the symbol epsilon, or some textbook they also use the symbol E. Okay, so what does strain mean? Strain means change in or change of length per unit original length per unit original length, change in length. So epsilon can be written as delta L by L. So this change of length or elongation that has happened, right, when you are stretching a body, when you are applying a external force, right? So now let's understand here the different types of stress strain. That is first important. So first we'll understand longitudinal stress and strain. Longitudinal means along the axis of the body. Suppose this is a body and you are applying a force, so internal force will be developed. Now I am not writing external internal, just this is the applied force on the body, which is definitely external and it is equal in magnitude to the internal forces. So we can say here the cross section area, if you see, this is the area of cross section which is perpendicular to the force, right? This force is acting perpendicular to the cross section. So if you take any cross section here, if you see, it is being, applied, the same forces are being acting at any cross section, right? You may cut it into different parts. Let's say here you separate it like this, and you can separate this part like this. Okay, so when you have to show the forces here, let's say this is the force, so here this is the force which is set here, and here also you apply, so this force. So these forces here, you can see that this is the external force you have applied, and this is the internal force which is developed in the material. So these internal forces which are developed is perpendicular to the cross section area. So this stress is called longitudinal, and this is the force by area of cross section, right? What is strain? So there will be change of length, so strain will be delta L by L, change of length per unit length. Okay, This longitudinal stress is also known as axial stress because it is acting along the axis. Axial stress. Now there is another thing that we should notice. There can be also change of diameter. So this longitudinal strain that we have taken, this is longitudinal strain. There can be lateral also, lateral or normal. Lateral strain here, strain or no, normal, not normal, lateral or transverse. Longitudinal is also known as normal, axial or normal. Why normal? Because it is perpendicular to the area of cross section, right? That's why normal. So transverse or lateral strain is the change in the radius or diameter. Let's say if you are counting this as the diameter, let us say this is the diameter D. Okay, so delta D by D. That's what is called lateral or transverse strain, right? Okay. Then this longitudinal stress or strain can be of two types. One is called compressive stress strain, compressive stress or compressive strain, and second can be tensile stress and strain. Tensile means you are applying the force to increase the length, like this is how the external force is acting, and in case of compressive you are trying to decrease the length, like this manner. Okay, the compression. This is just about the direction of the external force. So here you can say the change of length is going to be positive, strain is going to be positive. Which is strain? We are talking about longitudinal. Okay, longitudinal strain. Here also the change of length is going to be, here it is going to be negative because it is compression. So what about this strain? This strain is going to be longitudinal. As you compress, the longitudinal is going to be also negative. We are not talking about lateral right now. Lateral, of course, it may increase. Lateral and longitudinal strain will be opposite. In this case, diameter will decrease. So lateral strain, if you take, it is going to be negative. In this case, lateral strain should be positive, right? Diameter is increasing if you compress. Okay, so this is only about the direction of the forces, how the body is being stressed. So this is one kind of stress. Then let's go to the next. Next thing is about shear stress and strain. Shear stress and strain. Shear stress means it is responsible for changing the body, shape of the body. Okay. And here the force is going to act parallel to the surface. So shear stress, it is related with changing the shape of the body. Okay, and now if you apply force like this, what will happen? It can deform and its final shape may be like this. So some angle it will be, let us say rotate, angle theta. So there is a deformation happening here. This point has deformed here. So there is some delta x deformation has happened. Let us say this is the length. This length is L. So here force, external force acts. This is external force only. Acts parallel or tangential to the surface to the surface, and it is changing the shape. So we define the shear stress as this force divided by of course this is the internal force, but internal force is equal to external because there is a restoring force by the area. See, this area is known as shear area or shearing area which is parallel to the force. And here the shear strain will be defined the same way, changing length, but here the change of length is delta x here by original length, which is also tan theta. Okay, this is tan theta. So shearing stress is defined like this: shearing strain and shearing stress. Okay, right. Then let's go to the next. Third is about the bulk stress and strain. Bulk or volumetric stress. What happens in that? You will be changing the volume of the body. Suppose you apply a force like this manner. Everywhere you are applying force, external force. So what happens? The body undergoes deformation and its shape will decrease, it will become smaller. So let's say this is the area over which this body is spread, the external area. So here the forces are acting perpendicular. You will see that this force is like acting perpendicular. So here this shear stress, generally it will happen in gases. Why? Because the volume changes more in gases. Volumetric or bulk stress strain is significant. Stress and strain are significant as compared to liquids and solids. Okay, so again here this is written as pressure because this pressure is the same as this force by force. This force is again internal forces, right, which is equal to the external force. Okay, but remember, internal are restoring, external is just which you are applying from outside. And here strain, again volumetric strain, delta V by V. Magnitude wise, if you write, so it's minus, you can take, because it is decreasing, volume will be decreasing, right? Okay, now let's note some important thing. Suppose you are trying to make some holes in a thick sheet like this. For example, there is a thick sheet and thickness of the sheet is T. You want to punch holes like this throughout the sheet. You want to punch a hole. Punching of holes in a sheet. So punching of hole means you want to remove this portion of the material. So you are applying a force like this, but the force is acting parallel to this area. This area which is being removed, right? This is the area which is being removed. So force is like a cutting force, shearing force or cutting force are same. Okay, so this force will be acting in this manner parallel to this everywhere. So this will be like a shearing or cutting action will happen because of this. So that shear stress will be the force which you are applying by the shear area. Here the area will be shearing area. That shearing area is the curved surface area of the cylinder. Suppose the thickness is T and let's say radius of this hole is R. So pi r L, right? Because 2 pi r into L, that will be the curved surface area of this cylinder, outer surface area, which is the shearing area. Okay, right? So that's one thing that we should know. And what about the L? Here L is same as the thickness, right? So you can say this is T, thickness is T. So 2 pi r is the surface circumference into the thickness, which is like the length of this cylindrical portion. Okay, so we can use this method to calculate. And shearing stress is like the cutting stress. If you apply forces or stress lesser than that, you will not be able to cut the holes or punch the holes. You have to apply force larger than that. Okay. The next thing that we can note is, suppose for example, if you take a hollow cylinder. Hollow means it has internal radius and external radius, right? Suppose here this is internal radius R1, external radius is R2, right? So if you are applying some force in this, some force from this side you are applying, so the stress that you have to take is force by area. Here the effective area you have to take as pi r2 square minus r1 square. The effective area is the cross section area. This area you need to consider as the effective area on which the force or load will be acting, right? Okay. Then sometimes they will give that there is a rod or a cylinder is there. Interesting. And force is acting in this manner. And they will ask you to calculate along inclined plane. This inclined plane is making some angle theta here. What is the stresses along this plane and perpendicular to this plane? Okay, along this plane and perpendicular to plane, and this area is A here, cross section area of this. How will you calculate the shear and normal stresses? Yes. So let's try to understand this. First of all, this area which we are talking is like this, and you want to take first of area along this. So this angle is theta. This angle will be 90 minus theta. Okay, or you can say this angle will be also theta only. This area you can take as A dash. So A dash sine theta. A dash sine theta, that is equal to the A, that is equal to, so A dash becomes A by sine theta. Correct. Now on that area you have to study, right, what are the forces along this. So you need to resolve the forces in that direction. So if you have taken this and the force you are taking like this way, so this is making angle theta, so I think this theta, the same angle theta, right? We can resolve this force along this, and that become f cos theta perpendicular to this f sin theta. So if you want to take shear stress, you have to take the component of force parallel to that area by the shearing area, which is again area which is parallel. So f parallel becomes f cos theta, and this area, the dash area only, it has. So this shear stress which we are calculating is F cos theta by A by sin theta. So F by A sin theta into cos theta, which can be written as F by 2A sin 2 theta. Similarly, if you want to calculate the normal stress or longitudinal stress, it will be F sin theta, that force by this area which is A by sin theta. So it will become F by A sin square theta. Okay, so this is how we will be calculating the shear stress and normal stress across any other direction or any other plane. We will be able to calculate using this approach, right? Then let's go next. Sometimes they will ask which is maximum, for what angle it has to be maximum. According to that, we can say, suppose they ask shear stress has to be maximum, so it has to be 45 degrees. If they ask normal stress has to be maximum, then it has to be 90 degrees. According to that, we can change things into calculations. Okay. Right. Next, let us go to next. Now we can discuss about what is stress-strain relationships, Hooke's laws. What is Hooke's law? Relation between stress and strain. Stress-strain relation is given by Hooke's law. So within the elastic limit, stress is directly proportional to strain. So we can say stress is proportional to strain, right? So if you remove this, you will get a constant of proportionality that is called modulus of elasticity. This is known as modulus of elasticity, and for different type of stress strain it has different names. For example, if you take longitudinal stress, you take for longitudinal case, so longitudinal stress, this will become Young's modulus. Longitudinal strain, this Y will be called the Young's modulus of elasticity. In case of shear stress, this will be written as shear strain. So this factor, in different textbooks they have different symbol. For here you can write this as some symbol we can take, let's say eta. So this will be shear modulus of rigidity or elasticity. Then similarly, in case of bulk or volumetric stress is proportional to bulk modulus. Here I think they use the symbol G, not eta. G symbol they use. G, main textbook G. And for bulk modulus, they will use the symbol B. Okay. Volumetric stress and volumetric strain. This is called bulk modulus. Bulk modulus rigidity or elasticity. Okay. Now here you need to know, in general, this graph also some important points also will come, that is called inverse of this bulk modulus is also there. That thing we can see afterwards. Okay. First, let's understand that this stress by strain graph we are considering, it's like this, straight. But this straight graph that we are plotting, any point if you take, it's a straight line graph only we are taking. This tan theta, which is the slope of this graph, stress by strain, this is what is modulus of elasticity. Modulus of elasticity. And high modulus of elasticity means it's a highly rigid or elastic material. Okay. More slope means more elasticity. More elasticity means more intermolecular force. More intermolecular force. Right? Okay. That's what it is, I think. And it is also within elastic limit. Within elastic limits means within the elastic behavior. Within the elastic behavior. Okay. So that means we are considering that it is behaving like a spring. Material is behaving like a spring. So if you understand this with a simple example, let's say that this is a spring and you are applying some force. So you know the elongation, that force is equal to magnitude wise K into X. X here is elongation. So force is like external force, and you can also calculate the stress is force by area. So force is K X by area. Right? What will be the strain? Strain will be the change of length, which is X by original length. So stress by strain ratios. Stress by strain ratio, if you see, Kx by A by X by L. So it will become K by A L, KL by A, right? Stress by strain. So stress by strain is like Young's modulus or modulus of elasticity, KL by A. Isn't it? So from here the spring constant may be written as AE by L. AE by L. That's why for case of spring we see that K is inversely proportional to R. E is the modulus of elasticity, which remains same for a given material. It depends on nature of material. Nature of material. For a given material, this will represent its strength. So this modulus of elasticity also represent the strength. If you apply more force, then it may break. So it should be within that limit. Okay. Right. So from this graph, stress by strain graph, this also, if you draw that F is equal to Kx, right? This force. sometimes the graph can be force versus elongation, and in that case the slope of this tan theta is equal to k, and you know k is nothing but the E by L. So this is how they will be related. If they give force versus elongation, sometimes they will ask you to calculate elongation. So now you can calculate elongation, isn't it? Elongation is x here, so force is equal to k into x. So x will become force by k. K you substitute here, so FL by KT it will become. Okay. So this formula we will be using in many problems, elongation formula. This is elongation. Elongation. Because a rod is going to behave elongated just like a spring undergoes elongation. Because we are studying elastic properties, it is behaving like a spring. Okay, right? So then further in the next class we can go for the next more topics detailed into that. Thank you for your attention.